Hello, welcome to my channel. Today we are going to discuss about full wave bridge rectifier, which will convert AC voltage into DC voltage. In our previous video we looked at half wave rectifier where the circuit was very inefficient and the output was not usable. With this circuit we will utilize not 50% but the 100% of the input given to convert into an output. For this simulation we will convert 220 volt household voltage into 12 volt appliance voltage using a bridge configuration circuit. So before starting our simulation, let's look at our circuit on pen and paper. So initially we need a voltage source or an AC source with 220 volt as amplitude and frequency of 50 Hertz. This AC voltage, 220 volt AC voltage, will get stepped down into 12 volt using a step down transformer. This is the primary side, this is the secondary side. Then we will enter into a bridge configuration with 4 diodes. This is the load resistor. So at the input side we will have a sinusoidal voltage, a sinusoidal input. So on the positive peak or the positive portion of the wave, the current will flow in this direction. It passes through the first diode, then through the load resistor. There is a voltage drop, then it moves through this wire to the second diode, return back. Then on the negative peak or the negative portion, current passes through the first diode, through the load resistor, back again, then through this second diode and back. As a result we get output voltage on both portion of the sine wave. So our output voltage will be a 2 peak wave, but this output is not very reliable because it has very high ripple factor. As a result, to decrease the ripple factor, we need to add filtering. For filtering we use a component called capacitor. So we will connect a capacitor across the load resistor. So when the voltage is increasing, the capacitor will charge up. When the voltage is decreasing, the capacitor will discharge. Through this there will be a constant supply of energy to the load. As a result, your new output would be an almost straight DC output. But there is also a problem. When the voltage source is cut off, the capacitor would discharge. That means even after removing the source, there would be supply of energy to the load. As a result, some people add a resistor, a safety resistor across the load resistor, but that's not our major concern for this simulation. Alright, let's start our simulation. We start our simulation by adding a voltage source. Then we add 2 inductors for our transformer. Then since we need an AC voltage, we left click on our voltage source and set offset voltage as 20, offset as 0, amplitude as 220 and frequency as 50. Then we add a series resistance within the source as 0.1. We add a resistance value of 2 kilo ohms on our load resistor. We need some parameters for our transformer. For example, the primary voltage, secondary voltage, primary turn, secondary turn, or primary inductance or secondary inductance. LTSpice requires you to provide inductance. So if our primary voltage is 220 and secondary voltage is 12, 220 by 12, if we know Vp or Vs is equals to Np by Ns is equals to root over Lp by Ls. So as a result, 220 divided by 12 is equals to root over Lp by Ls, the whole square. 220 by 12, the whole square, is equals to 336, approximately 336, or 336 by 1. So the secondary inductance will be 1 millihenry and the primary inductance will be 336 millihenry on our transformer. Another important parameter we need to consider is magnetic mutual coupling coefficient, which is denoted by the letter K. So at the moment right now we have added two coils or two inductors and they are behaving as individual components. To act as transformers, we need to link between the two inductors. So we do this by defining what is K. K is the magnetic mutual coupling coefficient and we denote K as 1. That means 100% of the magnetic flux from the primary links with secondary. So if K is equals to 0.99, that means 99% coupling and there is a 1% leakage. So for this simulation we will consider at ideal and K will be equal to 1. We will go to LTSpice directives and include the label K1, L1, that means the primary, L2, that means the secondary, the value will be 1. We'll left click on our primary inductor. We set the primary inductor to inductance of 336 millihenry. The secondary inductor of 1 millihenry. We use spice directive and add our coupling coefficient value. If we set our probe on the source side, we can see a sinusoidal voltage with an amplitude of 220 volts, which is the source side, which is the source input voltage. If we set our probe on the output side, we can see a wave with multiple peaks. Even though this voltage is always positive, this voltage is constantly changing. We cannot provide this voltage to our appliances. As a result, we need to flatten the output voltage to get a proper DC voltage. For this, we will add a capacitor across the load resistor. Even though the peaks got reduced, there is still a visible amount of ripple, so we need to increase the capacitance value. By trial and error method, we set on a proper capacitance value. If we zoom through the waveform, we can see that the maximum output or the maximum value is 10.5 volts. We require 12 volts. So where did this voltage drop take place? The voltage drop was because of the diode. Per cycle, the per cycle 2 diodes are utilized. Each diode causes a voltage drop of 0.7 volts. Then 1.4 volt of voltage drop takes place per cycle. As a result, we need to compensate for this voltage drop. We do this by increasing the inductance of the secondary inductor in the transformer. Now if we run simulation again, we can see that our maximum output voltage is 12.65 volt, which is enough for our appliances. We can also set the capacitance to 500 microfarad. I think that's the proper appropriate capacitance value. Finally, our simulation is complete. We have successfully converted 220 volt AC voltage into 12.6 volt DC voltage, which can be used for daily appliances using a full wave bridge rectifier. Another full wave rectifier includes a center tap transformer, but I don't know how to simulate a center tap transformer in LTSpice. So that's it for today's video. Please like and subscribe. Goodbye.